Hello and welcome to the section 7.2 lecture today. Today we're going to be looking at solving equations with rational numbers involved, which will be a lot like yesterday's, but we'll have some more fraction problems that we get to deal with. So a lot of building on the last couple days and seeing where that takes us. Okay. So let's take a look. The first one here talks about solving an equation that involves fractions. And this is a very common strategy, but it says to solve an equation with the variable on both sides that involves fractions. One way that you can start, it doesn't say, or it says to kind of start like that's the only way that you can do it. It's not the only way. You could definitely go through this problem and turn all these into having common denominators if you wanted to, but this is a method that makes it a little bit easier. Okay, and call it what you will, but it's basically a way to turn everything into whole numbers as opposed to any fractions in the problem at all, which we can do as long as we do the same thing to both sides of the equation. So the first thing we want to look at is finding the least common multiple of all the denominators. All right, and it's basically like we're finding a common denominator. That's what we're doing. But instead of turning all these into fractions, we're going to turn them all into whole numbers and then work with the numbers from there. So it turns out that all my denominators, if I look at them, I have 10. Sorry about that. 10, 2, and 5. Are all my denominators, and of course I have a 2 over 1 here, but 1 isn't going to change anything when it comes to the least common multiple. So we find our least common multiple of all those, 10, 2, and 5, and we should kind of believe that it's 10, okay, because it is. Now, of course, you could use 20 if you wanted to. You could use any multiple of 10, but the smallest one is 10. And again, to find a common multiple of any numbers, you could just multiply them all together, but that would give us 100. And I don't want to deal with 100 because that's just going to make my numbers much bigger. Even though I could, it would totally work to use 100 as your kind of overall number. And the way that you'll see me do this a lot of times, if I were doing this process like on my own piece of paper, you see that they write it as 10 times this side and 10 times that side. I kind of think of it as just take this whole thing and multiply everything by 10. Okay, multiply all of it by 10, right? And that does some pretty awesome things. First, on the first piece here, when I multiply it by the 7/10 n, the 10s cancel out and I'm just left with 7 on top. So that's 7n. When I multiply it by the 3 halves, 10 and 2 reduce to 5 over 1, and I get 5 times 3, which is 15. When I do it on the next part, on the right side of the equal sign, 10 times 3/5 n, that's gonna 10 and 5 reduce to 2 over 1, and so I have 2 times 3 over 1. 2 times 3 is 6. And then the last thing I have is I have a 2, just a normal 2, and 10 times 2 is 20. So the one thing that you notice is it made all of my numbers bigger, which makes sense. I multiplied everything by 10. So that's going to make my numbers bigger. But more importantly, it gave me all whole numbers. No fractions are involved anymore. Okay. So now it's just a problem from our last section where we have the variable on both sides. So we want to get all our variables on one side, all of our numbers on the other, and then solve the equation from there. And they do it a little bit backwards here. They move the 15 over first. So they subtract 15 from both sides. That cancels it out over here, gives me a 5 over here. And because what I would say is I would do the variables first. They chose to do the numbers first. And it really doesn't matter. That's the, I guess, dirty little secret there, is you can move numbers first or variables first. It really doesn't matter. So then 6n minus 6n is 0. So I'm moving that 6n to the other side. 7n minus 6n is just 1n, or just n. Okay, and so n equals 5. So here it says, what is the advantage of multiplying both sides of the equation by the least common multiple of the denominators in the first step? Well, the big result here is that it eliminates all fractions. Because the alternative to that would be to say, okay, well, I know that the common denominator between the denominators that I have is 10. So if I wanted to do that, well, I guess there's a couple different ways that you could go at that. You'd either turn everything into a 10 denominator, or just deal with denominators as you need to, right? We don't have to have common denominators when we multiply or divide, but when we add and subtract, we do. So that's why it's a little bit less work than it seems to not eliminate all your fractions right away. But that is the advantage, is that it gets rid of all fractions and I just have whole numbers left. So what happens in the first step if you multiply both sides by a common multiple of the denominators that's not the LCM, not the least common multiple? So in other words, if I multiplied this by what I said earlier, we could use 100. Well, if I used 100, and this is definitely a different problem, well, same problem, doing it a different way. 7 times 100 divided by 10 would be 70, so it would give me 70n. 3 halves times 100, the 2 and the 100 reduce to 1 and 50. So 3 times 50 is 150. The 5 and the 100 reduce to 1 and 20. So I've got 3 times 20, which is 60. And then 2 times 100 is 200. So if I multiplied it by a different common multiple that wasn't the least common multiple, I still don't have any fractions. I still get rid of all of my fractions. I just have a lot bigger numbers. So it's kind of a trade-off. It's totally okay to do that. It's just not as, it doesn't make it as simple as it was before. It actually adds a step at the end because we'd be left down here, long story short, with 10n equals 50. Okay. So what happens? We still get rid of all fractions, so it still eliminates fractions. But results in bigger numbers. But I guess the most important thing is that it results in the same answer. So it is okay. It is okay to do. Okay, it does result in the same answer. Okay. So let's try that with these problems here. And again, I love that they give us no room to do this. That's lovely. Looking at my fractions here, they both have denominators of 7. So I don't have to work too hard to find the least common multiple. It's just 7. 7 times 1/7 is 1. So I have 1k. 7 times 6 is 42. 7 times 3/7, the sevenths would cancel, and I would just get 3k. And 7 times 4 is 28. All right, now I'm going to try to fit this in here. It's going to go over this next title, but bear with me here. I want to move the k. So I'm going to subtract a k from both sides. And I'll be left with negative 42 because these two cancel out. 3k minus k is going to be 2k plus 28. Maybe I'm going to move right over here. Now I need to move the numbers, so I'm going to subtract 28. I know that's hard to see. Let me switch colors here. So I'm going to subtract 28 on both sides. And now I do have to know negative 42 minus 28. Just combining those two things together, I'm going to get 70. Sorry, negative 70. And that's going to equal 2k. So then I divide by 2 on both sides to get rid of that 2. And it would look like k equals negative 35. So we would say here that k equals negative 35. And so again, this problem could have been done using the fractions without eliminating all the fractions. It might actually have been easier on this one because I only had one denominator and they were already common denominators. But using the method that the book taught us, I still think it's a valid method. Okay, the next one, what's the least common multiple? So we have to kind of think about least common multiple of 6, 2, and 4. What is that? Okay, so you got to think about multiples, not just the fact that they're all even. People would jump right to 6. Well, it makes sense. It's 6. It's got to be. Well, it's not. In fact, because I can't multiply 4 by a number and get 6. So I think about, my multiples of 2. So 2, 4, 6, 8. Think about multiples of 4. 4, 8, 12, 16. And I think about multiples of 6. 6, 12, 18, 24. Well, I notice that 12 shows up in both 4 and 6, but I don't have it yet in 2. That's because I didn't go far enough. So it looks like the smallest common multiple is going to be 12. So 12 is going to be that magic number that we multiply everything by, and it will get rid of all of our fractions. I don't like that one. Oops. So we're going to multiply the whole thing by 12 and see what that gets us. Well, 5, 6 times 12. 6 and 12 reduced to 1 and 2, so 5 times 2 is 10, so I get 10y. 1 times 12 is just going to be 12. 1/2 of 12 is, well, negative 1/2 of 12 is negative 6. And 1/4 of 12, or 1/4 times 12, is 3. Okay. And so verify those. Make sure you understand how to do those parts. I did go through them very quick, just in interest of time. But now I'm just solving a problem that we did on our last lesson. Okay, I'm going to add 6y to both sides. I'm going to move my variables together. And so negative 6y plus 6y cancel. 10 plus 6 is 16. So it's a 16y plus 12 equals 3. Now subtract 12 from both sides. Just double checking some things. Yep. So subtract 12 from both sides and I get 16y is equal to, that looks like a negative 9. And yeah, divide both sides by 16. And y equals negative 9 over 16. I guess I'm believing that. They usually like whole numbers, so I'm just double checking. 2, 10, that's 12, that's -6, that's 3. Yeah, I think so. I do all that math right. Yeah. Okay. Going with it. -9/16. Okay. All right. Then we can look at how to deal with decimals next. So here it says Javier walks from his house to the zoo at a constant rate after walking 0.75 miles, sort of, 3/4 of a mile. He meets his brother Raul. They continue walking at the same constant rate. When they arrive at the zoo, Javier has walked for 0.5 hours, half an hour, and Raul has walked for 0.2 hours, or a fifth of an hour. What is the, or I guess 2/10 of an hour? What is the rate in miles per hour at which the brothers walk to the zoo? So the biggest thing is that we can write this as an equation, and it's all kind of based on the distance equals rate times time, or speed times time equation. So we want to write an equation for the distance for the brothers from the brothers' house to the zoo, using the fact that the distance equals rate times time, just like I said. Let R be the brothers' walking rate. So again, they walk at the same speed, and they your book goes with a very similar approach, and I don't know if it's the best way to do it, but that's okay. So the way we break down this problem is that the distance to the zoo is the same. Yeah. Because we're dealing from their house to the zoo. And so looking at what's going on here, this is actually Raul's side. And this is Javier's side. Okay. And so Javier just walks for a half an hour. And Raul walks for 2/10 of an hour. And he had a 3/4 mile, 0.75 mile head start, is sort of where all this comes from. And so what they do is they look at the number of decimal places that they have. Okay, the highest decimal, or the highest number of decimal places they have is 2. And so they multiply everything in the equation by 10 to the 2 power, or the highest number of decimal places. That's how they figured out the 2 highest number of decimal places. And that's how they get rid of all decimals. Because when they do that, 100 times 0.2 just moves the decimal 2 times to the right, is 20. So 20R. Moving the decimal 2 times to the right gives us 75. And 2 times to the right gives us 50R. And then it's sort of like an equation that we saw the other day. Get all the variables on one side, numbers on the other, and then solve. So they subtract 20R from both sides, and then divide by 30. And so they find that the brothers' constant rate of speed was 2.5 miles per hour. And now again, I do mention that I don't know if this is the best way. I think decimals are pretty easy to use, especially with the aid of a calculator, which you probably would have used on this part anyways, 75 divided by 30. So why not use it for the whole thing? I think that it would be okay just to leave them as decimals, but we'll practice this same thing by using their strategy. So let's use their strategy on this one. It says Logan has 2 aquariums. One contains 1.3 cubic feet of water, and the other contains 1.9 cubic feet of water. The water in the larger aquarium weighs 37.44 pounds more than the water in the small aquarium. Write an equation to find with a variable on both sides to represent the situation. Then find the weight of 1 cubic foot of water. So that's going to be our variable. They tell us what to find. That's going to be our variable. We're going to use W for that. Okay. So we're going to deal with this in terms of weights. And it says that the larger aquarium weighs 37.44 pounds more than the smaller aquarium. And the larger one has 1.9 cubic feet of water. So the weight, let me think of the right way to say this. The weight of the larger one, or 1.9, that's our weight. The number of cubic feet times the weight of 1 cubic foot is equal to the smaller one plus the 37.44. 1.3 W plus 37.44. So that's the equation that we want to write. I'm a little bit unhappy with how that looks. And those equations are tough to write. So if you didn't catch that, I'll say it again. The larger one has to weigh more, and it weighs 37.44 pounds more. So we can't just say that the two aquariums have the same weight, because they don't. One's heavier than the other. And so we have to add the more than weight to the smaller one to make this equation equal. Okay. And now we want to do the same thing they did. We're going to, since I have 2 decimal places here, I'm going to multiply this whole equation by 10 to the second power, which is 100. And that's going to get rid of all my decimals. Multiplying by 100 just moves the decimals 2 places to the right. So this becomes 190 W. This becomes 130 W. And this becomes 3,744. So now I'm just going to follow my solving equation steps. I'm going to move my variables on one side. I already have my numbers on the other side. So 190 minus 130 is going to be 60 W equals 37.44. Oh, not point. Got rid of our decimals. 3,744. I thought I had it down there. I don't. So if we go 3,744 divided by 60, we get that W is 62.4. So 1 cubic foot is 62.44 pounds. So I would say on that one, definitely try to catch on to how the equation's set up, because that is a pretty acquired skill. But mainly I'm looking at the equation solving part of it. Can you solve that equation without too many errors? The next part is writing a real world situation. Again, just like we did in the last section, we're given an equation. We want to come up with, use our creative juices to come up with where does that come from. And so they use the example 0.95x equals 0.55x plus 60. And it says the left side has a variable term only, and the right side has a constant and a variable. And so they use like the left side to mean like the cost, the total cost for X items that all cost the same amount. The right side, they're thinking of, it could be a total cost of X items plus a flat fee. And so they use this situation, it says Toonie Tunes charges 95 cents for each song you download. Up with the downloads, charges 55 cents per song, and an annual membership fee of $60. How many songs must the customer download in a year so that the cost will be the same at both websites? So it kind of makes sense. And just in the interest of time, I'm going to go ahead and leave that one. You can come up with something. So what we're looking at is the same kind of situation that the left side has a variable and a constant. The right side just has a variable. So one of them has some flat fee going on, or flat some base charge. But yeah, I'm going to leave it up to you for how you want to write that. I would think I always think of like carpeting companies, installing carpet on problems like this. So this side has a base charge plus a little bit less for every say cubic foot put in or square foot put in, and the right side has just a price per square foot. A little bit weird with those being fractions, but if you had to turn them into decimals to make more sense of it money-wise, you definitely could. Okay? I believe that is it. So, an equation or a code word for today. Code word for today. I should just make you put in your story there. Nah, I'm not gonna do that. That would be mean. Let's see, what did we use last time? Okay, so we used that last time. Let's go with model. Because we're doing a lot of modeling of real world scenarios. So I think model sounds like a great code word. That being said, make sure you get the reflection done. And if you have any questions, don't hesitate to ask. Otherwise, we'll see you in class and have a great day.